Welcome back, everyone. It's my pleasure and honor to introduce our opening keynote speaker, Shumin Zhai, who has inspired me to be a text input researcher through his work. Shumin Zhai is a principal scientist at Google, where he leads and directs research, design, and development of manual and text input systems, interaction methods, and mobile haptics. His past research career has contributed to both theoretical models of human-computer interaction and broadly deployed practical user interface designs and product innovations. He originated the Shark project, which is also known as ShapeWriter at IBM Research, and a startup company that pioneered the swipe typing, also known as gesture typing keyboard paradigm. Just to emphasize on the impact of this work, this year's graphics interface-based human-computer interaction paper recipient will present a gesture typing method for smartwatches. Shumin Zhai received many prestigious awards for his research, including the ACM WIST Lasting Impact Award and an IEEE Computer Society Best Paper Award. He received his PhD at the University of Toronto in 1995. In 2006, he was selected as one of ACM's inaugural class of distinguished scientists. In 2010, he was named member of the ACM Chi Academy and a fellow of the ACM. In 2020, he was inducted into the University of Toronto's Engineering Alumni Hall of Distinction. Without further ado, let's hear from Shumin Zhai about his amazing work.
Thank you. Thank you so much. I am very honored and excited to give this keynote as a proud Canadian citizen and a graduate of a Canadian university. I'll talk about text input, which is something I've spent considerable amount of my career time on. But today I'll talk about it in a particular angle, focusing on the role of AI in the development of an advancement of the field, particularly a human-centered AI approach. Text writing obviously has a very long history. There's a variety of writing systems and technologies developed over the history of human civilization. And it is a history of co-evolution between culture and technology. Has always been like that. Before the current world of mobile-first computing, there were a long history of technology inventions and academic inquiries into the nature of writing. I put them in four categories. The first is dominated by how you arrange the keys on typewriter. It's quite common for a school kid to ask their parents or their teacher why the typewriter is not laid out from A to Z. Very innocent question, but actually pretty hard to understand. The researcher Hiso Yamada did the most thorough research on this, on the history of QWERTY versus its alternatives, in order to develop a Japanese parallel to the way of typewriter. The second category is how people actually learn, memorize, and type on a typewriter. And this was summarized in a book edited in the early 80s called Cognitive Aspects of Skills Typing. And then the third category is that what if you have more letters than your keys can accommodate? For example, in Chinese, there are 5,000 more or more individual characters. Can you have a typewriter that has that many keys? And from there, we can see some notions of AI, some notions of machine intelligence already become necessary to resolve ambiguities of the numerous Chinese characters within on a small keyboard. The fourth category is the so-called alternative and augmented communication for the motorly impaired, where you also see some of the early ideas of some notion of AI or machine intelligence that helps the motorly impaired users to type with prediction, auto completion, eye gaze, etc. Then it comes to the first era of mobile that is still dominated by direct manipulating individual characters and precisely manipulating individual characters by keys and stylus. Researchers already thought about back then, you can do this with more machine assistance in the form of statistical decoding, but generally it was not thought as necessary yet. Instead, researchers have spent time in thinking about how do you minimize the statistical travel distance of the stylus by rearranging the keys. Then it comes to the second era of mobile computing. Now, the manipulation of the small targets has to be done by fingers that are fat relatively to the keys. Indeed, this was viewed as the most scientific part of the iOS development in the early days. And there's a documented history of this for Apple to stop their engineering teams from everything else to pursue inventions of different ways of entering text on this finger touch screen. And when it was initially announced, when the iPhone was originally announced, it was widely viewed as a problem for lack of physical keys. In fact, critics believe it won't work. For example, Steve Ballmer, the CEO of Microsoft at the time, laughed out loud, saying it doesn't even have a keyboard. Well, 10 years later, touchscreen mobile phones have enabled whole new industries and ways of communication. This is just one example of WhatsApp alone sends messages in the order of close to 100 billion a day today. So how do we solve this problem? Well, here is a high-level principled framework for how these things are done today. So basically, it's all about machine intelligence, but also in consideration of the human factors involved in typing. The basic idea is that you have a user intention that is vaguely expressed by finger or voice or some other ways. In case of keyboard, it's by a set of touch points, the most basic way of doing this. And these touch points often are quite erroneous. The literal string of the output of the touch keyboard is often not what the user actually intended. So therefore, it becomes a problem of decoding. That is, decoding the information or the user's intention from noisy signal. And to do this is essentially a search problem or decoding problem in the sense that you try to find the best matching string with the given signal by essentially combining two models. One model describes how, given certain text, for example, a word, how likely, what are the distributions of words or spatial signals from the keyboard. And let's call that a motor control model. And the other is that given the context or some preceding words, what are the current words distribution? For example, you see how R, and the system already have a notion of the distribution, the words are likely to follow with certain distribution, like U, V, things, etc. In some special cases, so assuming the touch points are following a Gaussian distribution, which they generally do with a lot of caveats as documented in this paper. But if you assume there are a generic Gaussian distribution, and this problem actually can be solved quite elegantly by analytical methods following the Bayesian rule.
So there's a pretty analytical solution to this problem if you assuming a Gaussian distribution. Then that decoding process heavily depends on how good the language model provides the context and the prior distribution of the current word. So how do you do a language model? There are basically two classes of language models. The classic is n-gram models. You can think of it as a list of words and phrases. Obviously, you cannot cover all possible words you need and phrases you need, so there's always a backoff. The newer type of language models, which are much larger and much more powerful, is neural network models. Initially, it started with recurrent neural network models, and more recently, it's all moving towards transformer-based language models, such like BERT, GPT, and Lambda. Language models always has this issue of where does it come from? The training corpora quality with its own biases or profanity or noise are critical to the final quality of the language model, which need to be filtered and which need to be matched with the domain the language model is applied to. Then importantly, there's a training and test and dev set, which should be separated as all good machine learning needed. And finally, the model size matters to real-time compute, also often matters to its quality. And the primary quality of a language model depends on the perplexity of the language model. It basically says the degree of match between the model prediction and its training text. Of course, there's always the issue of concern that we should treat seriously in terms of privacy and personalization in language models. Here is a computational study that shows what language model-based statistical decoding can do. And this is a very simple classic n-gram model trained on the web out of 100 billion words and gets smooth and entropy prone and eventually has 160,000 words and 8 million bigrams. And by applying such a model using a simple statistical decoder, as I described earlier, in the simulation study, you can see that it would reduce error rate from some nearly 40% down to single digit, like 5 to 6%. And further personalize the language model by blending a cache model, which is a model built of a moving window of the user's personal history, and the background model, which is described earlier. Then you can further improve the decoding accuracy. So then what else can machine intelligence do? Can you handle even greater ambiguity in the user's input? Can user doesn't even have to lift a finger? So here it comes to the basic idea of gesture typing. The theoretical motivation was how you design a user interface that facilitate this easy mode to a more efficient mode. Namely, the initial user action is recognition-based. You look and select individual letters, and it's outside in and controlled and closed loop process to the user. And this is what makes user interfaces easy. So here's how you type a word quick. That's conventional way. Then over time, the user can think of this as a pattern. And the pattern happens to follow the same pattern you tap on individual letters. So here's the letter, the word quick in a gesture. And then over time, it's mostly becoming a recall-driven process. Rather than looking at the keyboard, you're really recalling the word gestures. But then how do you do this? In order to go from one letter to another by a continuous trace, you got to pass other words, other characters that's irrelevant to the letter, the distractions to the intended letters. So here's what we did. That is simple AI. In hindsight, it was quite simple, but the paradigm was so powerful that even simple solutions could actually enable a very novel and advanced way of entering text. The basic ideas were using a language model, which was as simple as a list of words or a lexicon, and geometric pattern matching. This enabled the invention of gesture typing that was loved by the early adopters. And here's one quote from the early adopter called "Revolutionized typing is the understatement of the year. This technology should be part of every keyboard on all touch screens." Someone nominated these developers for a Nobel, no joke. This was in 2008. And sure enough, today it is practically on all touch screens. There are many, many versions and different technologies and different specific embodiments and implementations to this very idea. It's on all major operating systems and mobile phones. So what else can simple AI do to enable new typing behavior? One class of application is to push for new form factors of devices. I would only use one example, namely smartwatch. The idea is that on a smartwatch, your finger gets even fatter. How do you absorb that increased amount of ambiguity? And again, the same sets of principles I described earlier can surprisingly still apply. And what's particularly interesting is that if you compare this with the traditional direct manipulation interfaces, namely breaking down the keyboard into multiple steps, each step would require a lower resolution. And then you can do this, but generally in the order of single-digit word per minute. With static decoding, you can get this up to a much more practical speed.
A finger-operated keyboard that supports both touch and gesture typing with statistical decoding on a smartwatch. Just like on modern smartphones, users type one letter per tap or one word per gesture stroke on WatchWriter, but in a much smaller spatial scale. WatchWriter demonstrates the combination of human motor control adaptability with modern statistical decoding and error correction technologies developed for smartphones can enable a surprisingly effective typing experience despite the small watch size.
Surprising indeed. I personally was quite surprised this could be done. And I said earlier, I'm looking forward to the paper later today on this very same topic, continue to advance this field. Then what about completion suggestion by machine intelligence or by language modeling? Well, there it comes to some deep HCI issues in terms of whether the prediction or suggestion offered, whether its utility is a net positive, because there's cognitive, perceptual, and motor cost to attend the suggestion and evaluate the suggestion and select the right one. That process can be classically modeled by GOMS type of HCI models, would show you that it's not a simple equation, that often the utility is not necessarily positive. And the other dimension is that how assertive you should make your prediction. Should the system always present suggestions, or should it be, namely, more extroverted, or should it be less extroverted? And here is one study showing that this sets of phenomena about the use of language model for prediction. And my colleagues at Google Brain and Gmail figured this can be done with modern language modeling. They used a bag of words and RNN language model initially to power and embed previous messages in an email, as well as the subject line of the email, and then combine that with the language model trained on email corpuses and predict the likely phrases you may need. And importantly, this manages the triggering rate or the assertiveness quite well. And furthermore, it only offers one suggestion inline, and only offers them when the utility is sufficiently high. Namely, it saves you many words, multiple words. And this is one of the most popular and successful AI applications in recent products. Then the next question is that, can we take this further? Can we write, can AI write autonomously without users' intervention? And the answer is no. And that's not without any human input, supervision, or training by developers and engineers on a particular language corpus. You can't, AI cannot do that, cannot write. And furthermore, it may not be even desired, because such a fully autonomous system could carry its own bias and lack of authenticity and accountability. So there's sets of AI principles that we all have to follow. Here's a demo of the Gmail auto reply that does write full sentences by looking at previous patterns and give you pre-prepared multiple choices. And you can always choose not to select any of them and just type by yourself. So in this sense, in the very small amount of composition, it is possible, again, with user's choice, it is possible to do it automatically. And then, and you may ask, what about all these wonderful technologies or powerful technologies in automatic chatbots? And here's what was announced about a week ago by Google, called Lambda. Lambda stands for Language Model for Dialogue Application. Importantly, it is designed for dialogue application, not for autonomous writing. And here you can see from the dialogue. The purple is the human input, and the gray box is what Lambda talks back. As you can see, the answers of Lambda is quite sensible. It's very much human-like. It even has sometimes some sort of humor in it. And this was all extracted from large amount of training by the language model. So how did the language model work? And this was the original paper published last year that documents how such large language models can work. There are several key points to such type of technologies. The first one is that it's trying to be human-like. And what researchers found was that to be human-like, there are a proxy to that is a combination of sensibility and specificity. So if the answer is sensible judged by human and it's also specific, then it's very much, to a very large degree, is what human conversations like. And this was tested on fairly large-scale experiments. For example, the model Mina has a SSA score of 72%. And in contrast to human, this was blind testing by, if you carry a conversation by a human in the same sets of tests, and then you'll find the SSA was about 86%. Again, this was last year, and it probably has got a lot better today. And the next key point is that such a measure correlates with perplexity. And that's a key to the training of such language models. This measure, SSA itself, is a human evaluation metric. And you pull crowdsourced workers to give ratings to each turn of the conversation. But then this measure was found to be strongly correlated with perplexity. And perplexity is the degree of match between the model and its training data. As you can see from the figure in here, different systems has different degree of perplexity, which generally, the lower the perplexity, the higher the SSA scores are. And this enabled the researchers to turn this human-like metric, SSA, into perplexity, and perplexity can be automatically calculated in a large training corpus in the training process. So Mina's training set contains about 40 billion words. Again, this was last year. And now it's many times larger. And a large amount of training data, the Mina using evolved transformer architecture that abstract and condense these 40 billion words into 2.6 billion parameters. And these parameters is essentially the model's memory or understanding. How you define the two is somewhat philosophical. But nonetheless, this is how such a model can carry a conversation that's human-like. Then there are still open questions. This was again designed for dialogue, for question and answer systems, and potentially can be used also for search and assistance type of technology. But can you turn such technologies to completely writing for the user autonomously with no use? Like can such models eventually be applied to writing, say, an email on my behalf by looking at my past emails and just write autonomously? And I'll say, no, there's no evidence that it truly understand the user intentions to that degree. And there's no evidence for that yet. Besides, we have to take responsibility seriously and follow the AI principles. That is, it has to be accountable. It also has to give the human enough control. And as a more relaxed version of this question is that can transformer class of language models such as BERT, GPT, or Lambda can be pre-trained on a very large text corpus and then fine-tuned on, say, my individual data, and then write on my behalf and prepare some version of a message ahead of time. That's actually quite possible, but there's a lot of HCI work needs to be done in terms of how to, first of all, how the model can truly reflect my intention given all the context it knows about me. How do you do this privately? And how do you make it easy for the user to proofread it, to revise it, or even to rewrite it? And how do you make this process to be less costly to the user so it's worth it? One can think of human analogies to this. That is, all US presidential addresses are written by presidential speechwriters, but they are distinctly the president's speech. And the relationship between the writer and the speech giver are perhaps a lot more than simply just understanding from text, from previous text. That's why many presidential speechwriters eventually become major politicians or commentators themselves. I also often think about this dilemma, my own dilemma, in terms of interaction between me and my tax return. So for example, I switch every few years between hiring an accountant to do my tax return and then flipping to doing it myself. The reason is that when I do it by my accountant, I still have to spend a lot of time understanding it and preparing the data. But on the other hand, when I do it myself, I find, well, this process is too tedious. So there's this trade-off that goes back and forth, and sometimes the automated side wins, and sometimes the self-driving process wins, at least for me. So I also wonder if you carry this conversation with Lambda, what it would be like. This is my answer, but I wonder how Lambda would do. I haven't got a chance to try that. So in conclusion, human-centered AI has been essential in advancing textual interaction. In the long past, for things like AAC or Chinese text input, and then for the past decade or two by researchers in the HCI field and in the machine learning field to design and invent new ways of writing. And it also offers new exciting opportunities, especially by the more recent, very large neural network-based language models. And it has been and will be critical to get the HCI aspects of this right in order for them to further advance towards some sort of writing assistant. Again, I thank you for inviting me to giving this keynote. And this work obviously is not possible without many of my co-workers at different institutions, such as Google and formerly IBM Research, Linköping University, where I visited and met my then student Perola Christensen, and later the Shapefighter Inc. company. And it goes beyond this list of co-authors. And now I can possibly answer some questions live.
Thank you, Shumin. Thank you for the excellent talk. If there are any live questions. If not, we received some questions through our YouTube channel. Alec Jacobson asked that, will we ever move on from QWERTY layouts? Suppose most typing with respect to 7.6 billion people is finger on glass rather than two hands on keyboard. Will we still be stuck with this legacy layout?
Well, thank you. That's a great question. I wonder if I have a slides on that. As you can see, I rushed through more than a decade of work. And some of the important aspects of it I did not touch on. That the question is an excellent one. It's still a central question to text input research. Part of the invention of gesture typing was actually came out of our early work on optimizing touchscreen keyboards. The QWERTY was designed partially by accident, but partially it is not a too bad accident for two-handed typing. The goal of Christopher Scholz and his colleagues in the 1860s were designing a typewriter or inventing a typewriter out of wood models. And these wood models get jammed, the wood hammers and the mechanism tend to be jammed quite easily. So they tried very hard to separate the consecutive hammers onto the two sides of the keyboard, so that when one moment you hammer on one side, and the next moment you're likely to hammer on the other side. Therefore, they don't get jammed easily. This happens to be pretty good for two-handed typing. Not necessarily good for because it encourages the alternation between left and right hand, which is one of the 3 or 4 factors later was realized to speed typing. Other than that, you can there's other factors like the particular sequence or the use of home row or load balancing or particular output sequence and so on and so forth. These factors were not taken care of that well by the QWERTY layout. But the fact that you can alternate between left and right frequently was a good design for two-handed typing. But then when you get to the gesture keyboard or touchscreen keyboard, it becomes much less clear. For two-thumb typing, it might be still pretty good. But for one thumb or one finger or one stylus typing, it was bad, which was the motivation for some of the early work my co-authors and I have done. This is the more recent work we did, is that can you further optimize it for not only the travel distance, but also for the clarity of the keyboard, particularly for gesture typing. If you look at this lower right corner, this is the original atomic layout. The word writing has a quite rich pattern to it. Therefore, it's much easier to recognize for the computer. More importantly, it's also easier for users to remember, to recall. On the top is sets of on the top is middle and top right are sets of new designs we did a few years ago that made this word, let's say, taking the word OR and OUR as example. On QWERTY, OR and OUR are completely the same. But on this new layout, you can see it has different patterns. And we're still pursuing this line of work. But and a lot of this, interestingly, is using machine learning. But there's an additional challenge to this is that if you have a new layout, provided it has better clarity, better speed, better efficiency, and everything, it's also multilingual. So there's a whole lot of publications in this field by us and by many other fellow researchers. And how do you get people to learn it? And that's another central topic of HCI in general, that is this ease and efficiency trade-off, or this ease and efficiency progression. How do you accelerate that process? And that's another very interesting and very challenging topic that many, including us, are still pursuing.
Thank you, Shumin. I have a question regarding phrase completion. I was wondering that whether phrase completion can influence how people write. For instance, if you wanted to write something and the phrase completion gives you something quite similar, but not exactly what you wanted to write, do you actually pick that? And does that change your writing habit, how you write and how you express your views?
Yeah, that's a very deep topic. But first of all, as I said earlier, the Smart Compose initially started in Gmail and then now in many other applications. Including actually when I was preparing this slide stack, I actually used it quite frequently. That is, but the key to that is that they manage this user's ability to ignore it, to not listen to what it does, or to easily select it. So the utility function is quite high. It also gives me the ability, give me the user the ability to actually take it. And often the reason I take it not only is because of the keystroke savings, but because it's written generally very accurately, in the sense of it's the right grammar, it's the right spelling. Often it's actually benefit to people who are not a native speaker of that given language. So there's many benefits to it. But on the flip side is that, well, if you take all suggestions, then are you still writing? Is the writing still yours? And is there still information to it? A colleague of mine, actually, one of my VPs, were joking about his colleague was saying, well, our keyboard wasn't making aggressive enough suggestions, because when they use another product, the suggestions are much more aggressive. And my colleague joked, well, I saw you married to someone who's more thoughtful than that. It's a joke, but it reflects also when you take old suggestions, then maybe you're not thinking enough. So there's this trade-off in there as well. But also interestingly, you can also learn from, like, at least in terms of language, in terms of grammar, you can possibly also learn from the suggestions, because it's properly trained, when it's properly trained. when it gets enough information from the much larger corpus that a human can possibly ever read that much. So these are really interesting questions we'll continue to pursue, and these are still open, these questions.
Thank you, Shumin. There's a question on Zoom from Kellogg Booth. Kelly, I was just wondering whether you would like to unmute yourself and ask the question to Shumin directly.
Sure. Hi. So Shumin, there's a lot of discussion in the literature and everywhere else about getting rid of QWERTY on physical keyboards. And often the justification, or at least one justification, is, well, gee, we'd have to change all the keyboards sort of all at the same time. And what if different users, weren't ready to move from QWERTY? Now that we have most things are soft keyboards, with the exception, of course, of still our traditional keyboards, do you see the eventual demise of physical keyboards, everything moving to touch, and therefore everything being soft? And then we'd have user customizable or selectable keyboards where everybody could choose the layout that works best for them, or possibly even move between them depending on the task they're doing.
Yeah, Kelly, that's a great question, and that's a pursuit of many people still, and in history, and today, and I'm sure in the future. And again, we all are still trying, and we should try. We should keep trying. As you pointed out, on a touch screen, it's so flexible. You can just change the layout by a gesture or by a few taps. So why not? And in fact, there are Dvorak and other keyboard users today, and once they learn it, they all swear by it. Is that, for example, one interesting phenomenon is that for Dvorak, the learning speed of Dvorak, the ultimate speed saving on Dvorak may not be that significant, but the learning cost is actually much lower, which is quite interesting. I haven't seen anybody clearly documenting or explaining this, why it's much easier to learn Dvorak than to learn. It takes about 1/3 of time to learn a Dvorak layout than learning a QWERTY layout. So my own explanation is because the use of home row on Dvorak, which is much greater. So many words can type on the home row alone. So you don't have to move your finger up and down when you do physical typing, 10-finger typing. So and that means you can benefit quite early, and you only have to learn some common words to get those going, and then your average speed gets up pretty quickly. But then there's also hurdles. There's persistent hurdles, that so much so that there's a Stanford historian coined a term called QWERTYnomics. The idea is that social technical systems always evolves on a particular path, and there's a path dependency. There's strong path dependency on it. So once you lock onto that path and you evolve into a suboptimal system, and that cannot be undone, and that's also known as the locking effect. And his prime example is the QWERTY keyboard. He also has other examples like DOS versus other operating systems at the time, and VHS versus Beta as a standard, videotape standard. He was actually, his research was part of the Microsoft monopoly debate and court case as well. But interestingly, all his three prime examples, two of them no longer is true. Like today, we have more than DOS, certainly, and people did learn new operating systems because they are better. And also, there's no debate or no relevance of beta versus VHS anymore. So back to QWERTY, can we change that? Maybe, but the hurdle is high. And in fact, if you look at Hiso Yamada's work, he's the one who studied this most thoroughly. He went back all the newspaper and magazine articles since the 1800s and studied all the alternatives. And his goal was to develop a different keyboard for the Japanese. The idea is that, well, now when computer, he was a researcher at IBM as well as other places in the US. Then went back to Japan, and I was actually one of the first professors at University of Tokyo's computer science department. And his goal was to develop an alternative to QWERTY. So when typewriter comes to Japan, it won't have to make the same mistake as QWERTY. But then if you look at typewriters or keyboards in Japan, it's QWERTY. Another example of QWERTYnomics, because you don't get a chance. I also thought about, oh, my kids, when they grow up, they don't have to learn QWERTY. But then before I know, they already learned. So that's the all this, for and against factors. But thank you very much, Kelly. Nice to see you. This is such a good topic.
Thank you, Shumin. We can most probably take one more question. Carl Gutwin asked that, do people really use shape writing purely from memory? After 10 years, the only shape I can reliably produce without looking at the keyboard is my own name.
Carl, that's a great question. That's a very good one, very pointed. And the answer is complicated and it's nuanced. So first of all, yes, you remember more than you consciously recall. Professional motor skills are largely subconscious. And you can look at all modern neuroscience literature would point up to the same. People generally are aware of the goal and the plan of a motor skill, a motor program, but they're not consciously aware of the specific process. So in that sense, you might be doing more recall than you think. That's one answer. The other answer is that, well, no, not much, is because, again, related to Kelly's question, QWERTY is such a bad layout in terms of giving you clues, in terms of as a map to define the shapes in shape writing. And they are all zigzag. They're all zigzag gestures, and they're all very similar. So there's not that much shapes to recall. And that's another answer to it. But I'm actually looking forward to, I remember in the early days of the process of inventing, developing ShapeWriter, excuse me, I met another keyboard researcher who said, I told him my dream that one day there will be many PhDs who will do their dissertation on shape writing. He said, oh, he had that dream twice. His name is Daniel Gopher. But today, indeed, there are many PhD students who are doing this kind of work. And I hope they would answer your question better in the next few years. That is, how does the cognitive process really develop in more detail?
Thank you, Shumin. We have some other interesting questions on our YouTube channel. If you have time, maybe you can have a look at them after we are done with this session. Thank you again for your excellent talk and your impactful research. We're really honored to host you here.